Evaluating a point, taking an average, or calculating a definite integral might seem like entirely different tools from your calculus survival kit. But if you strip away the notation, they share the exact same mathematical identity. They are bounded linear functionals. Take a look at this coordinate system. To understand how these work, we first need a space to operate in, the space CAB. This represents the universe of all real-valued, continuous curves defined on a closed interval from point A to point B. Before we can measure anything in this space, we need a ruler. We use the supremum norm. Instead of calculating the total area under the curve, the supremum norm measures the size of a function strictly by identifying its absolute highest or lowest peak. Now, it is crucial that we don't confuse a function with a functional. A function is the curve itself. A functional is the machine you see here. It swallows the entire curve as a single vector input, processes it, and spits out a single real number, or scalar. Our goal in mastering the space CAB is to identify the specific structure of these functionals. We need to explain how they compress an infinite set of continuous data points into one stable, finite number, without the output becoming unbounded. If you feed a curve into a point evaluation functional, it reads a single coordinate. If you feed it into a standard definite integral, it calculates the total area. These represent two extreme ways a functional can behave on CAB. This presents a mathematical problem. We want a single universal formula capable of expressing every possible bounded linear functional that could ever exist in this space. The solution is the Riemann-Stieltjes integral. Notice the heat-mapped x-axis under this curve. Instead of integrating evenly along the standard axis, the Riemann-Stieltjes integral introduces a new function, w of t, of bounded variation. Think of w of t as a customized weight distribution. Where w of t slopes gently, the integral barely registers the curve. But if w of t forms a sheer vertical cliff, a step function, all the mathematical weight concentrates on a single coordinate. The integral suddenly behaves exactly like a point evaluation. This brings us to Ries's representation theorem. As the equation shows, every bounded linear functional on CAB can be represented by a Riemann-Stieltjes integral, and the norm, the maximum output of that functional, is exactly equal to the total variation of the weight function w. The power of this theorem is that it reduces an abstract operator into something tangible. The entire behavior of a complex functional is perfectly encoded inside that one single weight function, w of t. But proving Ries's theorem requires a specific construction. To mathematically define the weight function w of t, we are forced to test the functional against a discontinuous step function, specifically the characteristic function of an interval. This creates a domain error. By definition, our functional is only defined on CAB, the space of continuous curves. A discontinuous step function is an illegal input. The machine cannot process it because it lies outside the functional's original domain. So, how do we safely force a machine to accept inputs it wasn't designed for, without breaking its internal rules or changing its norm? We use the Hahn-Banach theorem. Hahn-Banach allows us to extend the domain of our functional from CAB to BAB, the space of all bounded functions. With the domain extended, the machine can process the characteristic functions required to construct w of t, while preserving the functional's norm. This extension is what allows us to bridge the gap between continuous functions and the discrete integrators used to represent them. We can now rigorously define w of t by its values at specific points, even though those points are identified using discontinuous step inputs. In this context, Hahn-Banach acts as the essential tool that permits us to probe the behavior of continuous functionals using the simpler, blocky geometry of bounded functions. Let's pull up a quick summary. We started with the space CAB, a universe of continuous curves, and saw how bounded linear functionals map those curves to finite scalars. Ries's representation theorem provides the blueprint for how those functional machines operate. And when we need to construct the integrator itself, the Hahn-Banach theorem provides the domain extension necessary to complete the math. If this breakdown helped you parse your real analysis lectures, hit the like button and subscribe. Let me know in the comments if you want further visual explorations of classic texts like Kreyszig or Rudin. Next time, we'll look at the geometric consequences of the Hahn-Banach theorem. We will see how extending these functionals guarantees the existence of flat hyperplanes that can perfectly separate convex sets in Banach spaces. Recognizing these abstract functional extensions clarifies the rigorous link between a space of curves and its underlying integrator. This foundation allows us to navigate the more complex geometry of higher dimensional Banach spaces.